All right, we are going to do the second section of 12.1, which this section, both days of it, day one, day two, are all about estimating limits graphically. I'm going to make a disclaimer right now that my laundry machine is really loud and can't seem to escape it. And I had started it before I realized I needed to make videos. So we're here, we're dealing with it. So if you hear some background noise, that's what it is. Okay. So let's go ahead and get started. So yesterday we looked at estimating limits at a point. We looked at a couple of different features that go with this. And so one of the things we saw is there were a couple of places where the limit did not exist. And I talked about one rule, but we're going to talk really specifically about the rest of these rules and the different ways to know at a specific point when is a limit not going to exist. So one of the key times that a limit does exist is if your graph passes smoothly through that point. But here are the ways and the times where it does not exist. Number one here, so the limit of f of x as x approaches c. So this is going to a specific point on a graph, does not exist if our function approaches a different value from the left than it does from the right. This is what we saw yesterday that looked like a jump gap, where my graph maybe went here, had an open circle on the same x value, it jumped up, and then it kept going a different direction. So if the limit from the left and the right don't go to the same number, if the graph is not smooth through that point, the limit will not exist. There is another situation here. If f of x increases or decreases, and we're going to say if it does this without bound. So this would mean that it goes to infinity or to negative infinity from the left or to the right of C. Now, one note about this is infinity is an answer. For that, you could put infinity as your limit, but so it's not the same as does not exist, but this is where infinity really starts to mess with your mind. So in this blue note down here, it says a limit is a unique number. So a limit itself should be I am going to 5. I am going to negative 12.2. So when we are writing equations like the limit as x goes to some number c of f of x equals infinity, we are not picking a specific number. Infinity is not a number. And so rather than that, we are describing the behavior of the graph. And so that means the limit doesn't exist. It's going toward infinity, but we don't actually get a specific numerical value for what that limit is. It just keeps getting bigger and bigger. So we're describing the behavior of the graph. All right, number 3. For number 3, the third situation we'll find when it doesn't exist is if our function oscillates between two fixed values. And we're going to look at on the next page, this lesson pretty much will be looking at oscillation and what that looks like. So those are all of our different cases for the limit at a point if it doesn't exist. If it approaches a different value from the left or the right, it increases or it decreases without bound, or it oscillates between two fixed values. And we talked about this note here. We're also going to review end behavior as we talk about limits at infinity. So hopefully, and I know this was always difficult for us, but hopefully you remember about end behavior. This is that idea of as I look to the right of my graph, as x goes to the right or to the left, as x increases or decreases, what is y doing? Is y going upwards? Is y going downwards, or is it leveling off? So for limit notation here, if the value of f of x as x approaches some unique number L1, as x increases. So as x increases, that's positive numbers. It's the right side of the graph. And if we see that our graph is trending towards something unique, we could write in limit notation that the limit as x goes to infinity of our function f of x is equal to whatever that number L1 is that it's going to. And then the way this would read is right here. So if you remember, if you feel confused right now, we're going to switch as we get deeper. As you move to Precalc, we're going to move into more precise notation. You might remember from the class earlier this is as x, we would say as x approaches infinity, f of x goes to, so f of x arrows something. This limit notation is the same thing in a more precise mathematical notation. Let's talk about negative infinity. If the value of our function approaches a unique number L1 as x decreases, so as x goes to the left, then we could say that the limit as x goes to negative infinity of our function is equal to L1, or L2 is just representing, it's our variable to represent a number, which is read the limit of f of x as x approaches, and oops, we've got a typo here, negative infinity is L1. So a couple of quick review before we finish is that our graphs are the times that infinity is going to show up in limits, or as we look at this, will depend on if we need to understand asymptotes. So if a function has a vertical asymptote straight up and down, that is going to be some equation x equals c. And if that's the case, if we have a vertical asymptote at x equals c, that limit from the left or to the right is going to go to positive and negative infinity, depending as we approach a vertical asymptote at a point, our function will drop down to negative infinity or positive infinity. And if we have a horizontal asymptote, this is the case within behavior where our graph levels off. And we're actually going to see in some later sections some examples of this. So if you're looking for something concrete, stick with me here and we'll see some more examples. All right, so we've got 2 short examples today. That's pretty much it for these notes. And we're going to look at what we mean when we say an oscillating function. So we are going to explore some fun today. I love these. So let's go ahead and look here at Desmos. Let's graph it. So with this, remember that when it asks you the limit in this section, we are working solely with the graph. You don't have to know how to figure out the limit at 0 by plugging numbers in yet. We're just using the behavior of the graph. So let's go to Desmos. All right, and we are going to type in y is equal to x times, oops, that's the dot, times, and then grab the sine function, sine of x. And you do want to make sure that you're in radian mode. So click that little wrench. It is radians is green. I'm good to go. Change yours if it's not. And whoa, this is a fascinating graph. So I would encourage you to take a screenshot and put that screenshot into your notes if you want to from here. So if we look at this right now, I can see part A asks the limit as x goes to 0. So as I look at my graph and I look at 0, it looks like the y value from the left and the right is smoothly passing through a point, and it's passing through the y value of 0. So we can use the graph to say, okay, the limit as x goes to 0, it's smoothly passing through the y value, and that y value is 0. All right, here's the fun part. I hope none of you have zoomed out yet. If not, that's okay. Let's do it now. Woohoo! If we zoom this out, oh my goodness, I love this function. It's crazy. As we zoom out, this function is bouncing back and forth, and it's getting wider as it goes. These just, I think they're so cool. Okay, nerdy moment. So as we look at this graph here, as it goes back and forth, this, you can see it as we zoom in a little more, it is bouncing up and down. And so as this graph is going further, it is pinging from a negative number to a positive number, a negative number to a positive number, and it is going to do that infinitely. And so our options for limits at infinity, as I look at B and C, the options are the limit as x goes to negative infinity. It can be a singular number that it's leveling off at. It can be positive infinity, or it can be negative, but it cannot be both. And so this would be the an oscillating function. When we look at infinity, because it's bouncing back and forth, I cannot peg, it's not going toward only positive infinity or only negative infinity. This is a limit that does not exist. So we would say D and E. Same, so the left side, that's all these numbers over here. Remember, the left is the negative numbers. And so as we go out, it's getting wider and wider out of our zoom. As I look at positive infinity, Desmos is a really great way to do this. Let's look at our graph. What is happening? Do a crazy little zoom here. Can't even see it anymore, but it is, oh, I don't know what I just did. It is bouncing back and forth. The numbers are getting bigger. It's oscillating between positive and negative numbers that are getting bigger and bigger. So we would say this, again, the limit on the positive side also does not exist, D and E. Alrighty, let's look at another one. So number 2 is x times the cosine of 1 over x. So it's x times the cosine of 1 over x. Okay, so let me hit the home button. That zooms us in a little bit more. When we are home, you can see here when I'm at this kind of nice like -20 to 20 zoom, it almost looks like a straight line with a little bloop in the middle as it goes forward. And so we're going to use that as we look at these different values. So as we look here, let's actually jump to parts E and part F. So first, as I were to look at x going to -infinity, so imagine I'm going to just start scrolling through my negative numbers. Where is this graph going? As I keep going out further, the graph is going downwards and the trend is consistent. This is heading toward -infinity. So we would say the limit as x goes to -infinity of this function is -infinity. The trend is downwards. Positive infinity, we can use Desmos. I'm just going to the left, zooming out a little bit. This graph is growing upwards, so this limit is going to positive infinity. Okay, now let's look at 0. So it had that little wave like I told you, and when we look, this is crazy, but it starts oscillating, and this function is now oscillating back and forth, but these curves are starting to get smaller. And if you look here, I have zoomed in really close, and it's going to oscillate back and forth, but those numbers are getting consistently smaller and smaller. And so this would be the case where it is oscillating back and forth, but those oscillations are starting to converge. They're starting to get closer on either side to 0. So I could say as I got infinitely close to 0, this limit is going to go to 0. So just so you know, for this section, this is it. We're really just looking at those kind of exception cases. When does it not exist? And then also, because we've done so much work with end behavior before, I'm not going to talk as much about the limits at infinity, but in a separate video, if you are curious, these are some extra practice problems. If you're just looking for more limits and more examples, if you feel like you've been having a hard time, the right side is looking at the limit at 0 of the function and then the limit at positive infinity. So it just gives us some more practice. I am going to make an optional video that goes through these, and I'll post this in the links as well for the day. As a reminder, for today, there is one other required video, and that's going to be 12.1 day 3. I've just broken it up into smaller bite-sized sections. The next one is also pretty short as well. Let me know if you have questions, and then come to office hours or email me if you need some help from there.